Welcome to Engineering, Mathematics and Modeling Week 2, where the first topic will be the cross product. In the previous week we saw the dot product. That was one way of, a form of multiplication that yielded a scalar, and in the cross product, a completely different product, we'll see something different. First, the definition. The cross product of vectors, which we denote by a times sign and b, is a vector which is perpendicular to both a and b, and its direction is determined by the right hand rule, and I will show you the right hand rule in a minute, and its magnitude or modulus or length is given by, so the length of A cross B is equal to the length of A times the length of B times the sine of the angle theta, so the angle between the two vectors. Now, so we know its length and we kind of know its direction. So let's say we have a vector A here, we have a vector B here. The cross product will be a vector that is perpendicular to A, but also perpendicular to B. And I know it points, well, upward in this drawing, that if I take my fingers, curl them from A to B, my thumb points upwards. So we start with our fingers pointing in A, curl them to B, and the direction of the cross product is in the direction of our thumb. And this right hand rule you see in different areas, and especially in electromagnetism as well. So we know its length and we know its direction, but like with the dot product, the formal definition isn't the easiest way of calculating this. So let's say we have a vector A, which is ax, ay, az, and I have a vector B, which is bx, by, bz, and there's a formula for the cross product which now will not make a lot of sense intuitively, but once we get to determinants, there's an easier way of calculating this. But cross product A times B is equal to ay bz minus az by. So this is already the x coordinate of the cross product. Az bx minus ax bz and ax by minus ay bx. And one thing to note is that the cross product is indeed a vector. Where the dot product was a scalar, the cross product is a vector. And this, if we have two vectors, this is how we can calculate it. I'll give an example. Let's say we have 2 minus 3, 1, and we have minus 1, 2, 5, and we calculate the cross product using this form here. Then we get ay times bz, so minus 3 times 5, minus az, so that is 1 times by, 1 times 2. Then we get az, which is 1 times bx, is minus 1, minus ax, which is 2 times bz, 2 times 5. And the last one is ax times by, so 2 minus 2, times 2, sorry, 2 times 2 minus ay, which is 3, times bx is minus 1, minus 3 times minus 1, and together this gives, so minus 15 minus 2 is minus 17, minus 1 minus 10 is minus 11, and 4 minus 3 is equal to 1. So this is the practical way of calculating a cross product between two vectors. It has some properties. Well, we knew that for the inner product, the order of the vectors didn't matter, so it was commutative. So if we look at A times B, and is this equal to B cross A? Well, no. So if I start with my fingers at A, curl them to B, my thumb goes up. But if I start at B, curl them to A, my thumb goes down. This is a bit hard to show, but the direction will be reversed. So the cross product is not commutative. It is, however, it has the property of distributivity. So distributivity, B plus C. So if we have a cross product like this with a sum between parentheses, this can be written as A times B plus A times C. And there's some other properties in combination with an inner product that are written in the book. We also have that if we have a constant times a vector and have the cross product with the vector, we can take this constant and move it in front of the cross product. And this is something that is used by the book a lot. Now, what we see here is that the angle, we take the sine wave, the sinus function of the angle. And if we start at 0, pi over 2, pi, 3 pi over 2, and 2 pi, we see that for an angle of 0, that the sine is 0, of course this extends further, and that the magnitude is 0. So effectively, if the length of a vector is 0, the vector is equal to 0. So if the angle between the vectors is equal to 0, these two are in parallel. And specifically, if we take our unit vectors, so this will be x, y, and z axis, if we have our unit vectors I, j, and k, if we take the cross product between I and itself, it will yield 0 because these two are in parallel. The same goes for j, and the same goes for k. Now, so these are 0, but something, well, special happens if we look at, for example, I cross with j. Now, these are unit vectors, so their lengths are equal to 1. If they are perpendicular, if the angle is 90 degrees, the sine of 90 degrees, or pi over 2, is equal to 1. So we know that I and j are perpendicular to each other, but if we use the right-hand rule, go from I to j, it's in the direction of k, but it is also equal to k, because the length of this vector equals 1. It is in the direction of k, which has also got a length 1. Now there are two other identities. I can start in j, turn to k, and I will go in the direction of I. And if I go from k cross with I, we get j. These are identities that the book uses to prove basically this way of writing out the cross product. But you are free to use this. There are a couple mnemonics. One is the determinant, which we'll learn about in probably week 3 or 4. but there's also a way with crosses. You'll see that if you search for it on the internet. But this is something, well, you don't have to memorize. There are ways of memorizing it. So the cross product, it yields a vector. We know its length, we know its direction with the right-hand rule, and a more practical way of calculating it. And this is our first topic, cross product, and we'll continue with matrices.